Okay, so today we will discuss the last topic in Chapter 5, coordinate systems. Okay, since our scalars can be real or complex, so I would like to use f, right, to be R or C. Okay. So whenever I mention f means that it's possibly just a set of all real numbers, or it's just a set of all complex numbers. Okay. All right. Now let be an n-dimensional vector space all right, and the B a basis for V. Okay, so now by theorem 5.2.2, right? For each vector V in the vector space, there exists unique scalars. Okay, under vector space, I have to say over F. Okay, over F. Okay. So there exists unique scalars, alpha 1, alpha 2, up to, oh, by the way, I have to explicitly write down the basis vector in B, right? Yeah. So there exist unique scalars in F such that V can be written as a linear combination of the okay, so V can be written as a linear combination, and the coefficients are unique scalars. Okay, so the bracket of, so that we will call, so this is defined to be alpha 1, alpha 2 of alpha n is in the n-dimensional Euclidean space. And so this is what we call the B coordinate vector of V relative to the ordered basis B. Okay, so this is the data, and then with the basis B, then we set up a coordinate system. So we call the B coordinate system for the V. Now suppose we have C okay, I use B prime, right? Because Later on, I will reserve C for other use. U1, Un, another basis for V. Okay, so another basis for V, and from the B-prime coordinate vector of V relative to B-prime. Okay, so the question is, what is the relation between the B coordinator and the B prime coordinator? All right? Okay, so we recall the B prime coordinate function okay, the B prime coordinate function with is an isomorphism. Okay, by theorem 5.2.3 plus 4. Okay, so with V B equal to alpha 1, alpha 2. So if the B coordinate vector of V is equal to this vector, then we know the V is equal to summation. It's a linear combination, okay, of the basis vector Vi in B. Right? And so we can applying the B prime coordinate function, okay, on both sides. Okay, so now, we will apply this B prime coordinate function on both sides. Okay, so we have on both sides. And because the B prime coordinate function is an isomorphism, so it has linearity, so we have the summation of I equal to N alpha I Vi and B prime here. Okay, this is bilinearity of the B prime coordinate function. Okay, and then we can write it in matrix form. 1. Okay. So we put all the column vectors. So the column vector is just the B prime coordinate of Vi, right? So the ith column would be this B prime coordinate of Vi. So the first column, second column, etc. up to the nth column. And the coefficients is put together here as a column vectors. Okay? All right, and so this is a matrix. This matrix will be give a name as B to B prime. And here, this is B and the B. And this vector is just the B coordinate vector of V. So where is defined to be okay. It's an n times n matrix. All right? And call the transition matrix. All right? Call the transition matrix from the B coordinate system to the B prime coordinate system. Okay, so it's easy to read from this notation, right? So it's a matrix we call transition matrix from the B coordinate system to the B prime coordinate system, because it will transform the B coordinate vector to a B prime coordinate vector of the same vector B. Okay, and from here, from this definition, you know how to construct such a transition matrix. Why? How? Well, it consists columns, right? And each column of this transition matrix is the basis vector Vi in the basis B, right? In the basis B, and you take their B prime coordinate vectors. So you take the B prime relative to the B prime. All right, so we have a theorem 5.3.1, which is called change of coordinate system. So if we have B prime, they are basis for an n-dimensional vector space V. Then for all vector in this vector spaces, the B prime coordinate is related to the its B coordinate by a transition matrix. And B to B prime is the n times n matrix. With V1, V2, up to Vn, Bn basis vectors in the basis B. All right, so let's take an example. Consider two bases okay, for R3 1 minus 1 0 2 0 2 minus 2 3 minus 1. This is the basis. Well, it's easy to check whether this is a basis, because by theorem 5.2.1, this is 3 columns form a basis of for a basis for R3, if and only if we form a matrix by using these 3 columns, then this matrix must be invertible. Okay, and you know the technique to justify whether a 3 by 3 matrix to be invertible, right? Very easy by using the Gauss Jordan elimination. Right? So the reduced echelon form should be the identity matrix. That's easy, right? You just do the, especially 3 by 3. So you know how to check them. Okay, and B prime is another basis for R3. Okay, so now things V1. Now we have to, because to find this transition matrix, we have to find the B prime coordinate of each basis vector in B. Okay, so that V1 is equal to okay. So V1 is a linear combination of U1, U2, and U3, and the coefficient is in this B prime coordinate. So linear combination can be written in this matrix multiplication. Any questions? Do you have any question about this? If you do, please raise your hand. I will explain. Otherwise, I will assume you know what it means. What is meaning? So this one, so B2 is also equal to, and this is V2 B prime, And last one, U1, U2, V3. The reason why I use the matrix form is because that we don't know this, we want to compute, right? So that what we want to is I want to find this transmission matrix. Okay? And we want to know what is that? Like our question is to find out this transition matrix. But to find out this transition matrix, we have to find these three B-prime coordinate vectors. Right? So they are unknown. So we don't know this, we don't know this, we don't know this. But we know that they have this relation because V1 is a linear combination of U1, U2, and U3. And the coefficient is inside this B-prime coordinate. This is the meaning of B-prime coordinate, right? Similarly, V2 is a linear combination of U1, U2, and U3. And the coefficient is inside this B-prime coordinate of V2, etc. Okay? So now we have a matrix equation. That we put them together, U1, U2, U3, and you have the unknown, V1 beta prime, V2 beta prime, V3 beta prime. Together, this is equal to V1, V2, and V3. Okay? So I put these three equation into one equation. Okay? Because this matrix times this column is equal to V1 here. And this matrix times the second column give us V2, etc. And this is unknown. So we have to solve. But these two matrices are known because they are given here. And we are sure that this is invertible matrix and also this is also invertible. Okay? So that you can take the inverse of this into there. So of course you should have a solution. But we don't do that. We will use Gauss-Jordan elimination, right? So here is the way we do it. All right, and so to solve the matrix equation, okay, we reduce the augmented matrix. So our augmented matrix is what? It's U1, U2, and U3, V1, V2, and V3. Okay, so this augmented matrix is 3. Okay, and reduced to by elementary operation. Because we know this is invertible, so when we do the reduction by using Gauss-Jordan procedure, this matrix become to the identity matrix, right? Before we do anything, we know this should be the result. Okay, so we should have. All right, and I just copy what I have done. Okay, and so we know the unknown matrix is here. So this is our unknown matrix. Okay, the solution. Okay, so this is our okay, and we have done. Finish. So we just turn the problem to metric equation. Okay. And once again, we employ the technique we learned in chapter 1. We are now at the end of chapter 5, but we still need the technique in chapter 1. Always go back to chapter 1 to find a path to solve your problem. Okay, so that is the so in this example, you know how to do it, especially if you're dealing with basis for Euclidean spaces. Okay. Okay. All right, so now our next question is, so now what is, right, you know the transition matrix from the B coordinate system to the B prime coordinate system, right? Now what is the transition probability from the B prime coordinate system to the B? Well, you can do the same, all the same thing, right? You can do that. But we want to know the relation of this transition probability, transition matrix to this transition matrix. Okay, so here is the way we look at our coordinate function. Okay, so let's see observation. That the B coordinate function is from V to Fn. Okay, and also the B prime coordinate function is also V to Fn. Okay, right, and both are isomorphisms, as we know. Okay, so let's see that the coordinate, you can see, to do the coordinate change from the B coordinate system to B prime coordinate system, actually we do this way. This is the inverse. So, and do, okay, so that is, if this is V here, so this is B prime. So a B prime coordinate, all right, this B prime coordinate must be a big of some vectors be here. And now from here, we go to B prime. Okay, so from this composition, we know that the composite inverse, which is F, goes to, right? So this composite isomorphism gives us so it's the isomorphism from the B coordinate system to the B prime coordinate system. Okay, and so it's just the matrix representation. Okay? It's just the matrix representation of the isomorphism. Composed with, okay, relative to, okay, so just that, just the, right, of this isomorphism from Fn to Fn. Yes, please. Yeah, sorry. Okay, let me see. Yeah, so, oh, yeah, okay, and thank you. Yeah, thank you for the typo A there. Okay. It seems that I did not write the dimension unconsciously. Maybe I unconsciously observing there is a typo A there. But thank you for that. All right, so okay, so from this discussion, we know that actually this transition matrix is indeed the matrix representation of this isomorphism. Okay, right, from Fn to Fn. So the inverse. Now, so the inverse of this isomorphism gives, all right? So that what is the inverse? The inverse of right? The inverse, it's easy to know that it's inverse, okay? So you just reverse the order and then take the inverse. So this is a, so this is give us from B prime to B. Okay. Okay. So this isomorphism is from the B coordinates to B prime coordinates. So the inverse is from the B prime coordinate to B coordinate. All right? So, and since this matrix is the, so, which has as the matrix representation. Right? Because it's from B prime coordinate to B coordinate. So this, its matrix representation should be this transition matrix from B prime to B. Okay? But this matrix is a matrix representation of this isomorphism. So the inverse of this matrix becomes to the matrix representation of its inverse. We have proved that in a theorem in section 2, right? So what is the theorem number? (5.2.c). Okay, so in 5.2.c, if A is the matrix representation of an isomorphism from Rn to Rn or from Cn to Cn, then A is invertible, and its inverse, A inverse, is just the matrix representation of the inverse of that linear transformation. So by theorem, we see that this matrix representation should be the inverse of this matrix representation. Okay, so we can answer the question there that this transition matrix from the B prime coordinate to the B coordinate is actually the inverse of the transition matrix from the B coordinate system to the B prime coordinate system. Okay. All right, so we answer our question here. Any questions? Right, so this is the reason why I create a notation like this one. This is B prime to B, and here is B to B prime. Right, and they are just reverse to each other. Okay. Okay. The next theorem is an extension. All right, so maybe I will say here. Okay, remember theorem 2.4.12 says that to specify a linear transformation from an n-dimensional vector space to an arbitrary vector space. You can do the following way. First of all, you pick up a basis for this n-dimensional vector space V. Okay, so this basis has n vectors, say V1, V2, V3, up to Vn. And then you from the codomain W, which is an arbitrary vector space and can be not finite dimensional, arbitrary. So from the codomain W, you pick up n vectors, W1, W2, W3, up to Wn. And then you assign Wi to Vi. And that's it. You will completely specify the linear transformation T. There is no other choice. You have one and only one linear transformation. Have this specification. So this is exactly Theorem 2.4.12. And we use this theorem many times. Okay. But this was extension to what? In some sense, in that you can do the same thing for arbitrary linear transformation from arbitrary vector space, not necessarily finite dimensional. Okay, so this is theorem. Okay, the author of the textbook put this theorem in the textbook. Well, I welcome his inclusion, but that actually we will not use this theorem later, but will be helpful. Oh, I found a typo again. I forget the S. Okay. Okay, a linear transformation. I forgot the S. S is missing in my notes. Okay, so a linear transformation from a vector space V, so not necessarily finite dimension, arbitrary vector space, to a vector space W is completely determined. Okay, by the image of any basis for the domain V. The images by the images. The images can in turn be arbitrary Okay, so the proof, the procedure for the proof of this extension theorem is similar to what I have done for theorem 2.4.11 in chapter 2. Basically, if you read my proof in my lecture notes, basically the same. But there is one concept called indexing an infinite set. Okay, and that you may not be familiar with this concept. So, so let me just put a draft of the proof. Well, not complete, but it's exact, almost the same, right? Except the beginning only, because we are dealing with a linear transformation from arbitrary vector space, not just finite dimensional vector space. Okay. So we let B to be Vi, and I is indexed by an index set I, B, and so here I will say indexed basis for V. Okay, so we have to use index basis. And this I can be arbitrary index set. For example, I can be the set of all real numbers. So the index set will be uncountable. You even cannot count it. Okay, so it's called uncountable. Or the index set can be just the set of all non-negative integers, 0, 1, 2, 3, etc. So it's countable, but infinite. Okay. So where I is an index set, right? And this index set can be finite or infinite. Okay. Now, the reason why I don't want to drive more on vector space which is not finite dimensional is that if we consider arbitrary or if we consider a vector space which is not finite dimensional, can we define dimension for that vector space? How? You cannot just put infinity, because infinity in number theory have many ramifications. You may have countable infinity or uncountable infinity. For example, the size, okay? Suppose every set has a size. The size of all integers. And you consider the size of all real numbers. For your heart, you will think the size of all real numbers is much, much, much bigger than the size of integers, right? Of the set of integers. So even though the set of all integers is finite, the set of all real numbers also finite, but they have different size from your heart. And how you distinguish between those infinity? How do you do it? So this question puzzled mathematicians at the end of 19th century, more than 100 years ago, because now we have 2021, right? But before 1900, say 18-something, 1885, 1896, whatever, more than 100 years ago, mathematicians try. They think we have to deal with this problem. We have to make distinction between the infinity to describe the set of all integers, and the infinity to describe the set of all real numbers. Because from our hearts, they are different. Okay, so that's why they developed the theory of a new modern theory for set called set theories, and also they build the logic which lay the foundation of modern mathematics, and will influence the science, not only the mathematical community as all the science, especially in physics. Okay. Right, so that is a big story, and I think I don't have enough time to deal with this topic in this course. Right, so I just ignore, right, forget to deal with the problem of how to define dimension for a vector space. But I can give you the conclusion. Yes, the answer is yes. You are able to define dimension for an arbitrary vector space, even they are not finite dimensional. Okay? But they have to go through some rigorous procedure in modern set theory. Okay, and we will not to do that here. Okay, all right. So anyway, but the proof will be okay. So I just realized, say, I have an index basis. Okay, so the basis has been indexed by an index set. Okay. All right, and so the counterpart is, all right, so Vi just basis vectors in this basis. So Vi, I also in index set. So we have a collection or a set of vectors also indexed by the same index set. Okay, so be an arbitrary index set of vectors in W. Okay, and because they are just indexes, so it's possible for different index. For I and the J are different index, but Wi, Wj would be equal. It's possible, okay, because they are index set. Okay. All right. So if they are, you find. Okay. All right. So with this setting up, then the specification that TVI equal to WI for all I in the X will uniquely determine linear transformation. Determine T from V to W. Right. So this is exactly the meaning of the statement of the theorem here. Okay. Hi. So for details, please see the proof. My lecture, no? Which follow the similar procedure as that in the proof of theorem 2.4.12. Okay. All right, so I think I can give a remark here. If B and two bases for a vector space. Okay. It can be shown that there is a bijection F from I to I prime. So basically, I and I prime, so if we have two indexed bases, I'm sorry, I forgot to put. So if we have two indexed bases for the same vector space, okay, then it can be shown that there is a bijection F from I to I prime. So you can regard the I and I prime to be the same set because you have one-to-one correspondence and until. Okay. And because of this property, a vector space has a dimension. Okay. And so the dimension will be the size of any such index set. Okay. Right. And in set theory, they have a mechanism to deal with the size of a set, especially those sets which are infinite. Okay, so they define different notation for infinity, different meaning of infinities. Okay? But for our purpose, that would be good enough. Okay, so that if in the future, if you do the research and you need a concept that every vector space has a dimension, then yes, the answer is yes. Okay, and so you can associate the dimension for any arbitrary or arbitrary vector space. Okay, and the basic the basic concept, fundamental concept is here, that if you have two index spaces for the same vector space, then the index set are bijective to each other. Okay. Oh, all right. So let's take 5 minutes for a break. Okay, so we will proceed our discussion. Okay, so now we will focus on a linear transformation. So now T okay, a linear transformation from an n-dimensional vector space, okay, to an m-dimensional vector space W, so it's V. Okay. So I have to highlight the dimension here. And the finite dimension is very important, and n-dimensional. So that the domain and the codomain are finite dimensional vector spaces. Okay, so we just focus on such a linear transformation. All right, and the B, so B be a basis for V, right? And because V is n-dimensional, so the size of the basis is n. C W 1, 2, W M is a basis for W. Okay, so once again, because the dimension of W is M, so the size of this basis C is M as required. Okay. Now, for all V in the domain, all right, and the B coordinate of V is alpha 1, alpha 2, up to alpha n. Okay? So, with this B coordinate, so we can recover V, right, by linear combination of the basis vectors in B. So that would be summation of alpha I and the Vi. Okay? So once you know this B coordinate vector, you should be able to write down this equation here. All right, so now we check, so now we check the linear transformation T on both sides. Okay, and the bilinearity, we have, okay, and again, we do it many times. Okay, so oh, by the way, okay, I think, okay, this is not our interest. Our interest would be from here, and then, so taking T on both sides. I can say applying, I'm sorry. Give us this one, and taking C coordinate. We have because all these vectors are in the codomain W. So, and we select C as a basis for the codomain W. So that's C again. See here. And now the C coordinate function is an isomorphism. So we have this one. C here. Okay. So now this is a column vector, right? In Euclidean space, and also each of the bracket T of Vi sub C is also a column vector. Now, so we can write down a matrix line. Okay, so now we are able to write down a matrix equation. 1 T V2 C T Vn C, right? This matrix, and the alpha 1 and okay, and so this will be denoted as C and V. Where we define this matrix. So what is the dimension of this matrix? Because the C coordinate vector is m dimensional, and the B coordinate is n dimensional. So this matrix is m times n. Okay. It's an m times n matrix. Okay. And called the matrix representation of the linear transformation T relative to the basis B for the domain and the basis C for the codomain W. So that's why I put the B and C in the subscript here to indicate that the first one is the basis for the domain. The second one is the basis for the codomain. Okay. Right. So, and it's indeed a matrix. It's m times n matrix. All right. So it's called the matrix representation of T of this linear transformation. Okay. And from the definition, you can see how to build this matrix representation. Okay. Column by column, right? Column by column. Okay, so this is, if I write it here. Okay. So from here, from this equation, you can see that we can see that the vector B can be replaced by its B coordinate. Okay, and the image TV in W can be replaced by the C coordinate. So these two coordinate vectors, they in general have different dimension. This coordinate vector has n dimension. This coordinate vector has m dimension. And their relation is that you can be transformed from this B coordinate to the C coordinate by a matrix, by an m times a matrix. And this matrix will be called the matrix representation of T relative to B and C. Okay, and so with coordinate systems, linear transformation from arbitrary vector space to, from n-dimensional vectors to m-dimensional vector space can be described as a linear transformation from the n-dimensional Euclidean space to the m-dimensional Euclidean space. And here we have a matrix. So once we render to here, now we can apply matrix theories, everything we learned in the first four chapters up to determinants, right? Chapter 1 to chapter 4, all the materials to deal with linear transformations. Especially, more often, we can apply the Gauss-Jordan elimination procedure, okay, to our problem. To solve problem for general linear transformation from finite dimensional abstract vector space to finite dimensional abstract vector spaces. Okay, so this vector space can be function spaces, okay, or many different objects according to the area you are studying. Okay. Okay, so that this is very important because if you want to use computer programming so well, MATLAB, even though there are a lot of database to deal with, they do it numerically. Remember that? Of course, some mathematicians use mathematics as something that they can handle with functions. But basically, the baseline is that they're dealing with numerical because our computer is digital. They can manipulate only numbers, real numbers, basically. Actually, not real numbers, right? Because they can't. According to a procedure, they can only dealing with integers. Okay, but dealing with integers will be good enough. Okay, so to solve any problem in linear algebra by computers, you have to resort to matrix theories. So coordinate system is very important. It's lay your foundation for you to solve your problem numerically. Okay, and that is that is why we can solve big problems in linear algebra. Okay, by using modern computers. Okay, so you have to know this transformation. Okay, all right. So now, if you fix a basis for the domain and you fix a basis for the codomain, then you have the matrix representation for such a linear transformation. But what if you change your basis? Okay. then you would have different metric representation. Okay, and so the question is, what is the relationship between these metric representations? The reason is that if we want to have a representation, we want this representation as simple as possible, right? We want this representation as simple as possible. And this makes the solution for your problem efficiently. For example, if you don't do a good representation, you may need a month to solve a problem. But if you found a very simple representation, you probably solve your problem in 1 hour. If you are an investor to a company who can do things very well, then the value of that company will be huge, right? So, okay, so the problem is that, but we don't know what is the simplest representation, right? Not yet. We don't have a clue up to now. But anyway, as a problem solver, you should select a basis for the domain and a basis for the codomain as a starting point anyway, and to get a metric representation. And from that, you try your best to find another representation, which is much simpler than the one you select at first. So this is the usual approach for you to deal with your problem. Otherwise, you will never get into the solution. You have to start your procedure, right? No matter how you do it, you should just get a start. All right, so now we have to deal with the problem that suppose we have all right, so question. So what is the relation between two metric representations, T for B and C, and T for B prime, C prime? Okay, so our question is this one. So if suppose you have, so now we have B prime basis for V, okay? C prime basis for W. Now, okay, and for these two bases, we have coordinate change, right? We just studied. So we say, all right, we have a V and it's easy to write down. Okay. Similarly, we can write coordinate changes for vectors in the codomain. So we have now also we have okay, and then you know how to compute okay, well, just expanded. And for different coordinate system, okay, this is what we have. So if we select B as a basis for the domain, C as basis for the codomain, then we have this matrix representation. And the B coordinate vectors were transformed by this matrix representation to the C coordinate vector of the image of V here. And similarly in here. So we have all these data up to now. So now we want to know the relation between these two. Okay? Good. Now, now the images is in the codomain. So we now have T, V. Now since TV C prime is equal to C prime C of T C here. And of course, and this is TVC. We apply this one. So this is C prime C, and this is T B C, and this is V B. Okay. And now the VB C prime to C T, right? But the VB can be obtained from B prime, V prime here. Okay, so this is just the coordinate change, right? This one is coordinate change, and we use the matrix representation here. Okay, so the C coordinate of the image of V is equal to the matrix representation relative to basis B and the basis C. Right, and multiply with the B coordinate of V here. This is from here. And then this B coordinate of V can be obtained from the B prime coordinate of V by using this transition matrix from B prime to B. Okay, and so now we start from here, end up here. So this one, right? The product in the red parentheses compared with this one. So that would be equal to this matrix. So that T becomes to read this identity is very simple. What is that? You select B prime for the domain. You select C prime for the codomain. So now, yes, you use the B prime as a basis for the domain, and then you do the coordinate change to the B vector. So after this matrix representation, the image will be in the C coordinate. All right, in the C coordinate of the codomain. And then you do the coordinate change from C coordinate to C prime coordinate. And that is here, where you do here. So B prime to B, B to C, and C to C prime. This is quite natural, right? So it's not hard to memorize the relationship. This is very complicated, you know, but with the notation like this one, is much more easier to read through it. So you have this relationship. Okay? And so we have theorem 5.3.4, the matrix representation of a linear transformation. All right, so the data is that T is a linear transformation from an n-dimensional vector space V to an m-dimensional vector space W. And B prime basis for V, C prime basis for W. Okay. Right. So with all this data, so they are unique M times M matrices. Okay, so we have two matrices, T defined to be T V1 and T B prime C prime U1 T U2 T, UN. Okay, so they are unique M times M matrix. So we have two, right? B equal to V1, V2 up to Vn, and V prime equal to U1, U2 up to Un. So they are such that and okay. So first of all, we have matrix representations for each pair of bases. Okay, so we have this one, and the matrix representations can be obtained column by columns. Okay, column by columns. Yeah. Okay. So they are unique matrices. And the relationship between these two matrix representations is that okay, right? So we just prove this theorem. Now we will consider special cases of linear transformation. So let T be a linear transformation from a vector space V to V itself. Right? Suppose that, so the codomain and domain are the same. In this case, T will be called a linear operator on V. Okay? In this case, in many applications, we will select a same ordered or indexed, maybe I will say a same indexed basis for the domain V and the codomain V. So now V is served as domain as well as codomain. So of course, in general, you can select a basis for domain V and another basis for codomain V. That's fine. Okay, and then you can have a metric representation relative to these two bases if they are different, right? So, but in many situations, we will select a same index basis for the domain V as well as the domain and as well as the codomain V. We will select the same. Okay. Okay, so with respect to to B, T has a metric representation when V is n-dimensional. Okay, so, and we define B to be BB. So if we select the same basis B for the domain V and for the codomain V, then this metric representation will be denoted just by using a B here. Okay. So once you see here, you know T is a linear operator on an n-dimensional metric space, and the same basis is selected for the domain as well as for the codomain. Okay. Right, and then we have T V B is equal to T B V B for all V in the vector space V. All right, so there are only one basis is considered B here. Okay, and furthermore, that makes things simpler. So that also, and if the basis is V1, V2 up to Vn, then the metric representation becomes to T V1, use the B, T V2, B, T Vn. Okay, so V1, V2 up to Vn are basis vectors in basis B. Okay, and the images, because the image is also in V now, so and we take the B coordinate of the image of V1, B coordinate of the image of V2, etc., to construct this metric representation. All right, and with respective to another basis, B prime for V, so we have TV equal to T B prime, and the V B prime for all V in V with the metric representation equal to T maybe I write U1. And so T U1, B prime, T U2, prime, T UN. Okay. So you have another metric representation like this one. Okay. And so what is the relationship between these two metric representation? This one and this one. Okay. Well, so now these two are related by B prime. So this is actually okay. So now because that this metric representation actually is B prime, right? Because the codomain and domain use the same basis, and this is also B prime to B prime. So the first part, you use B prime coordinate. After this change of coordinate to the B coordinate, and apply to this metric representation relative to B. Okay, so you get the image now is in the B coordinate. So you do the change of basis, change it to the B prime coordinate. Okay, so finally you get this one, this metric representation here. But in this situation, you see that this one is the inverse of this. Okay, so that you have inverse of that. Okay. So now we have a theorem about the basis change for linear operators. Okay. So T, a linear operator on an n-dimensional vector space V. Okay, and the B prime basis for V. Right? So then we have B prime is equal to inverse. Right? So we have that. Okay, so there is a relationship that you can obtain the B prime metric representation from the metric representation relative to basis B by a matrix P and its inverse. So that there is a definition called similarity. So an n times n matrix, okay, A is said to be similar to an n times n matrix B, okay, denoted as A similar to B if there exists an n times n invertible matrix called P such that A is equal to P multiplied with B multiplied with P inverse. Okay. So two n by n matrices A and B are similar. Say A is similar to B if and only if A can be written as P times B times P inverse for a invertible matrix P. So you compare this one, you can see that the matrix representation of T relative to basis B prime is similar to the matrix representation of T relative to basis B. Okay, so for a linear operator T, matrix representation relative to different bases were similar to each other. Okay, so they were similar to each other, and the matrix, the invertible matrix used would be the transition matrix for coordinate change. Okay, for coordinate change. So that is the we have that. And similarity actually is an equivalence relation. So, yep. Really? Oh. 5.5? Oh, yeah. 5. Sorry. Thank you. Yeah. I don't know why okay. Yeah, it's 5. Thank you. Good. Okay, so similarity among matrices. Among n times n matrices has the following 3 properties. Right? So for n times n matrices, A, B, and C, first is about refractive property. A is similar to itself. Why? This is because A can be written as, okay? So this is identity times A times inverse of identity. Second, symmetric. Okay, so if A similar to B, then B is similar to A. Why? This is that the reason is that here A is similar to B if and only if A can be written by this product. Okay? For some invertible matrix P. But this is equivalent to saying that B can be written. So if we multiply P inverse here, you get A and the P here. Right? So you multiply P here and P inverse here. Okay, and then P there. So you can cancel these two. You get this one. And so this can be written as P inverse of A and P inverse inverse. Now the invertible matrix required is the inverse of P. Inverse of P is also invertible again. Okay, so this is true, and so it's transitive. If A is similar to B and B is similar to C, then A is similar to C. Okay, so the reason is that A equal to B A is similar to B and B similar to C if and only if A can be written as P, B, P inverse, and B can be written as Q, C, Q inverse for some invertible matrix. This is P and Q. Okay, so you have P and Q here, and so that you can plug in Q, C, Q inverse, P inverse here. So you have PQ and C and Q inverse, P inverse, and this is PQ and the C, and here is PQ inverse. Okay, so the invertible matrix needed is just the product of these two invertible matrices. Okay, so we have the transitive property. So the conclusion is that similarity is an equivalent relation on the set of all n times n matrices. Okay, so that is the case we have. Okay, all right. We introduce the concept of similarity from basis change of linear operators. Okay, from here. So now we may have a question that if two matrices are similar, can we create a linear transformation such that A is here and B is there? Okay, and also the P is served as coordinate change. Okay, a kind of reverse concept, right? Because we introduced similarity because of this equation, right? Okay, and so we define similarity for arbitrary matrices. Okay, and the question is just a curiosity, right? To say that once we have two similar matrix A and B, right, and have this equation, can we find a linear transformation T such that A is just this one, B is just this one, and P is this coordinate change? And the answer is yes, we can do. So that is the last theorem. All right, so let A is similar to Q, all right, with A is equal to P, Q, P inverse. All right, so now we want to create a linear transformation, right? So taking the columns of P to form, because P is invertible, so by theorem 5.2.1 we know its columns form a basis for the Euclidean space, right? So taking the columns of P to form an ordered basis B for the Euclidean space, then we have Q to be TB. Okay, so very interesting. If P, we select the column as P as the to form an ordered basis, then this Q will be a metric representation of a linear transformation, right, relative to this basis. And what is this linear transformation? Where T from Fn to Fn is a linear operator on Fn with the Tx is equal to Ax for all x in. So the matrix A is serve as the matrix to define the linear operator on Fn. Okay, so we reach our goal, right? So if but we have to justify this is true. Okay, so that this becomes to very interesting thing that that this becomes to T. So this is actually, you know, if A is this metric representation, so A is actually is the metric representation of the standard basis. Okay. So from here we know that A is the matrix representation of T relative to the standard basis. Equal S, which is just E1, E2 up to En. Okay. Right. So relative to this standard basis, then because that the x vector is written relative to the standard basis, and also this image is also written in the standard basis. Okay. That's why A is just the metric representation of T relative to the standard basis. All right, so this is A is the relative to, and the P becomes to the new basis. So the basis is obtained by taking the column of P, all right, as the basis, and the Q is T relative to B, and here is standard basis to there. So everything is done. Okay, so the important thing is to observe that once we write down a linear operator on the Euclidean space, then the matrix representation is just this A, is matrix A, relative to the standard basis. Okay, for Fn. Okay. Okay, so now, so P, because P is U1, U2 up to Un is invertible. Okay, so since P is invertible, its columns form a basis for Fn by theorem 5.2.1 before. All right, so by theorem 5.3.5 in above, okay, we have the standard. So the matrix representation of T relative to the standard basis okay, and so we just write the inverse there. And of course, as I just mentioned, this is A already, no problem. Okay, because of this definition. So this is A already. And what is that? So we have to compute carefully. And where? What is this? This is the vector in the basis. So that U1 take relative to the standard basis, U2 relative to the standard basis, up to Un relative to the standard basis. But if a vector relative to a standard basis is itself already, so this is U1, U2 up to Un, and this is just P. This is just P, right? Okay, so this is P. And of course, this is P inverse. And then you have nowhere to go. Because once you have A here, P inverse here, then this one must be Q. Because we have this identity. Okay? Because that, so this says that TB, it's P inverse A, P. Okay? Because you multiply P inverse here and P here, you can cancel them. So that this matrix representation is this one, and so this is Q. And we have done already. Okay? So we have achieved our goal, right? And our curiosity gives us positive answer, right? That whenever you have two similar matrices, then you can set up a linear transformation T so that A is a matrix representation of that linear operator T relative to a certain basis. Here, just the standard basis. And the Q will be the same linear operator relative to a basis. This basis is created by the columns of the matrix P. And that's it. Okay? All right, so I finished chapter 5 and stop here. Okay, thank you. Sorry about that.